Good morning. I see 23 of you has joined. Okay. So maybe if you are absent anyway, no problem. So I received 18 email with classwork from second semester. And yesterday there was 25 present in the class. So another 7 is missing. So may I know what is the issue? Or you are still on the way of sending emails? Already I see 23 has joined and I received 18 emails. So even if out of this 23, 5 of you didn't send me email. Okay. So these 5, can you tell me why you didn't send?
Sir, good morning, sir. Sir, I will send you within 2 days because, sir, I have seen, sir, you have give us time with 48 hours. Hence,
Yes.
Sir.
Okay, no problem. Okay. So it's good. So it's expected that those who didn't send yet, please send. Okay, and if you have any issue, then inform me. But hopefully there should not be any issue. It's regular activity. Okay. So any issue regarding yesterday's class, then you can talk, discuss. So yesterday we discussed regarding the little bit some recap on atoms, atomic structure. Then we quickly jump to the types of solid based on conductivity or electrical behavior, and these are conductor, semiconductor, insulator, etc. Then we discussed energy level, energy band. Then we tried to discuss the band structure of semiconductors. Then we have calculated the electron concentration in conduction band and hole concentration in valence band. Okay. So today we shall continue our discussion on same topic. Okay. So can you see my screen?
Yes, sir.
Okay. So today we shall start a continued discussion on the same topic. Okay. So we have seen that there was two types, mainly broad types of semiconductor. One was intrinsic semiconductor, another was extrinsic. In intrinsic, most of the carriers remains in valence band. However, based on the conditions, covalent bond breaks and some electron jumps from valence band to conduction band. Accordingly, electrons are available in conduction band. These are free electron for conduction. Similarly, the electrons leave from valence band, create one hole, okay, by each electrons. And we said that these holes are available for again conduction. But the difference is electrons possess negative charge, here hole possess positive, because shortage of negative means positive in this respect. But physically, actually, in valence band, holes are not moving. Actually, electrons are moving. Okay. So once the electrons jump from breaking a covalent band to the existing hole, then we say that the whole position of the electrons. In this way, hole moves. Okay. And in intrinsic semiconductor, actually, number of holes and number of electrons are same. This is because each covalent bond, each electrons jumps from valence band by rupture of a covalent bond, leaves one hole in the valence band. So, in principle, number of holes and number of electrons are same. Okay. And also, mainly electrons lie in conduction band for mainly like electron lie means free electrons available for conduction. Similarly, holes lie in valence band. So yesterday we have seen the expression of electrons so concentration in conduction band and hole concentration in valence band. So if you look, you see this was the expression for electron concentration in conduction band. Okay. So from this expression also, you see, if you can have a look here, you see, if value of EC increases, if this value of EC increases means it shifts in this direction, then physically say your valence band is here. This is your valence band. Okay. Then if EC increases, then the probability of jumping electron from here to here is less. That means electron concentration decreases. So you can see from this expression also. If EC increases, then this factor increases, but it possesses a minus sign. So the value decreases. So probability of electron concentration decreases in conduction band if EC increases. Similarly, here, similarly for here also, you see, if you go through this picture, no, this one, where is the picture? This one. If EV here, in that case, if EC increases, then probability, because if EC increases means gap increases. But here, if EV decreases, then probability of hole concentration decreases. But if it is EV increases, then gap decreases. So probability of jumping electron, that means finding hole here, increases. So from the expression also, you can see same thing. Here is the expression. Okay. You see in this expression, the hole concentration, if EV decreases, means gap increases. So if EV decreases, that means EF minus EV increases, and minus, so it's again the value of PC decreases. But if EV increases, then gap decreases. And here EF minus EV will be less for higher EV. In that case, value of e to the power minus this factor increases, because this, when this value decreases, that means less minus, so it increases. So if EV increases, then probability of finding hole increases. This expression also support this. Okay, so in intrinsic semiconductor, number of electron concentration in conduction band and here and hole concentration here is always same. This is because each electron jump from here through rupture of a covalent bond leaves behind a hole here. So এখানে একটা hole পাবে যদি এখানে একটা electron থাকে. So in this way they are same. Now from yesterday's class we have the expression for electron concentration in conduction band NC is equal to like this. গতকালকে আমরা যেটা দেখেছি where এটা ছিল constant. Okay. Similarly, expression for hole concentration in valence band. Yesterday also we have this expression. Okay. But in intrinsic semiconductor, these two value must be same. So we can write NC PC. NC means electron concentration, or PC means hole concentration. NC PC is equal to, that means just multiplication of these two. NC and B into this one. This is because EF cancel out. E power আছে যোগ করলে EF একটাতে প্লাস আছে একটাতে মাইনাস আছে cancel out হয়ে গেছে হয়ে গিয়ে এরকম একটা এক্সপ্রেশন পাওয়া গেছে common expression. Just simply we multiplied the electron concentration in valence conduction band and hole concentration in valence band. Okay. Again, EC minus EB is the energy gap, this value. So we can write NC is equal to PC. This is okay, no problem. Now we just changed the nomenclature. I for intrinsic semiconductor, then Ni is equal to Pi, again no problem. NCPC is equal to Ni square is equal to Pi square, no issue. Then from this expression we can write NCPC is equal to Ni square is equal to Pi square, like this. Okay. Or Ni is equal to Pi is equal to root over Nc Nv e to the power minus Eg by twice kT. Okay. Now if we put the value of Nc and Nv, then we can have an expression like this, where Me and Mh, these are effective mass of electron and holes. And yesterday also we highlighted this issue. Effective mass of electrons and holes are a little bit different. This is because mobility of hole is less. So mobility less means the mass is a bit higher. Okay. Why mobility is less? Because hole lies in valence band and electrons lies in conduction band. Okay. And when you apply bias or field, your electron will move faster in conduction band compared to the movement of electron in valence band. This is because valence band is highly occupied or traffic is higher. Okay, that's why the different order লেখা আছে MEMH. Okay, rest is okay. Then we can write an expression like this. The C is equal to all the constant except T. We take out T here, then e to the power this value minus Eg by twice kT. So this expression shows that if temperature is fixed, this T or this T, K is constant, then the intrinsic concentration is solely dependent on the gap Eg, solely dependent on the gap between valence band and conduction band. But if temperature is increased, if temperature is increased, then you see here minus is there. So if T means this value decrease, so this value of this factor increases, and here is directly proportional to this one. So again, value increases. So slightly increases. If temperature increases for a particular fixed Eg, then again intrinsic concentration increases. So intrinsic concentration depends on these two factors. One is temperature, and another is gap between the semiconductors. Okay. Now, phone is from the drawing. Okay, so sorry for the interference. Now, we'll see how Fermi level position or expression for Fermi level in case of intrinsic semiconductor. Okay. So yesterday we discussed about Fermi level. Actually, Fermi level is an hypothetical energy level. Physically, it does not exist. So this is your conduction band. This is your valence band. Okay. So this is your Eg. So electron will jump, only it will get energy of the order of Eg or higher. But if energy is slightly less than Eg, but higher than this value, that is EV, higher level of valence band, then it is expected that it will jump somewhere here, depending, or here, depending on the amount of energy. Okay, but it physically it cannot remain here. It will again come back. So it's a hypothetical level or positions. We can say that at absolute zero, if any electrons in the valence band or atoms have get energy higher than EV but less than Eg, then the position up to which it can jump, অথবা highest যে level maximum যেখানে এটা পাওয়া যেতে পারত, it's a hypothetical. This is EF. Okay, so physically it's not existing. It's a probability of finding electron at absolute zero, the highest level. Okay. Now let's see how Fermi level behaves in case of intrinsic semiconductor. In case of intrinsic semiconductor, we know Nc is equal to Np. Then we can put Nc is equal to, we have this expression. Then we have the value of Np, we can put this. Okay. So you can check this, or you can do calculation also. Okay. Then a simple mathematics. I have taken NC by NV, and you will have expression like this. Then again, এটা উপরে গেলে মাইনাস হয়ে যাবে, যদি করো তাহলে এর পাওয়ার এরকম চলে আসবে। এরপরে you take log from both sides, then you will have an expression like this. Okay. Then you rearrange and find an expression for EF. So EF is equal to EC plus EV divided by 2 minus KT by 2 log NC by NV. Okay. And this NC by NV is nothing but ME by MH, because rest all factors within NC and NV is same. So it will cancel out. So finally, we will have an expression like this. EF is equal to EC plus EV plus 3KT by 4. Now at absolute, if you consider or think about the ambience of absolute 0, that is T is equal to 0, then you will see EF is equal to EC plus EV by 2. This factor is 0 if it at absolute 0. It will cancel out. Okay. So in that case, if you draw the energy level diagram, you can see that, say, this is your conduction band, this is your valence band, this is the lower level of conduction band, this is the lower level of valence band. Then your EF will just lie exactly in the middle of these two. That is EC plus EV divided by 2. This is your EF, position of EF. The maximum electron can jump up to this. এখানে তুমি electron পাইতে পারতে. You could have found electron here. Okay. Okay. Now, if it is not, temperature is not 0, then you see that this factor MH and ME is not 0, so same. So this is not 1. Log 1, again, it could have 0. But since MH by ME greater than 1, it's greater than 1, because MH is higher than ME, effective mass, due to mobility. Okay. This is an estimated value. It vary. Okay. Say EC minus EV of the order of 1 electron volts, and KT is equal to at room temperature. Just say at around 25 to 27 of the order of this. So we can say that at room temperature, there is not absolute temperature is not 0. Then this EF slightly shift to the EC, slightly shift this direction. But it's very small shift, because KT is very small, and this difference is also very small. Okay. So slightly shift towards the conduction band if temperature increases. Okay. So you please check. And I am coming in 5 minutes. Please. Okay, so I am back. Now, Fermi level in semiconductor having impurities. Impurity means either N-type or P-type. You have added external atom within your pure system. External atom to create electron rich system or electron shortage system, so that either it can supply electron to the conduction band easily compared to the movement of electron from valence band to conduction band, or it can take electron from the valence band to create a hole in the valence band compared to the movement of electron from valence band to conduction band. Okay, so depending on the type of added material, যদি ইলেকট্রন রিচ হয় তাহলে সেটা ছিল এন টাইপ ম্যাটেরিয়াল, আর পি টাইপ বলছিলাম যে যদি ইলেকট্রন হোল রিচ ম্যাটেরিয়াল। ওকে, সো দিস ক্যান বি ডান বাই অ্যাডিং valence electron having valence electron 5 or 3 system. Okay, and normally in this impure system, if it is n-type material, that means probability of probability of finding electron in conduction band given by the donor impurity is many times higher than the probability of finding electrons in conduction band due to covalent bond breakage. Okay, because this donor impurity lies close to conduction band. Okay, say here, this is your energy corresponds to donor. Then probability of jumping from here, then here is higher due to short gap. Okay, so we can say that electron concentration in conduction band in case of n-type material is approximately equal to the number of donor impurity. That is, each and every atom, impure atom means added material, will give 1 electron to the conduction band. In that case, if Nd is the number of donor impurity added to your pure system, intrinsic system, should be equal to number of electron concentration in conduction band. Okay, so in an n-type material we can write, and this is the standard expression for Nc. Okay, electron concentration in conduction band. So in an n-type material, this should be equal to Nd. Nd is the number of donor impurity by added materials to supply electron to the conduction band, this one. Okay, equal to your Nc. Now we do, I did some calculations. Nc by Nd is equal to this, that, do simplification, then you will have an expression like this. EF minus EF is equal to EC minus KT log Nc by Nd. Okay, so you can we can say that in case of n-type material, say এটা ছিল আমাদের conduction band, valence band, conduction band, valence band, say এটা ছিল আমাদের donor level, then Fermi level will be just এটার নিচে, এটা ছিল EC, এরকম এটা hypothetical level, this is your EF, but it should be higher to Nd, because normally electrons rich atoms are available here. it will jump to conduction band as soon as it will have energy of the order of this A amount. But যদি absolute zeroতে this energy is lesser, then electron could have found somewhere here. Okay, so this is your sorry, not EF, this is EF. So in n-type material, EF will remain just above the ED and just below EC somewhere here. Okay. Now in case of p-type semiconductor, normally what we do, we add trivalent material in the pure system, and each trivalent atom will accept one or help or induce breakage of covalent bond here, valence band, and accepts the electrons, leading one hole here. Okay. So probability of from jumping here to here is less. Okay. So in principle, number of ED, this is acceptable level means EA. Say ED E A, this is EC, this is EV, this one. Okay. So in principle, number of acceptor atom, that is N A, should be equal to PC, because each acceptor atom will help to break one covalence bond here, leading one hole. Okay. To honest, okay. So in principle, PC is equal to Na, where PC is the whole concentration. PC is the whole concentration in valence band, and Na is the number of impurity. Okay. So normally we expect that EA somewhere here, so that it can easily accept electron compared to this level. Okay. So we can write this N is equal to এটা ছিল PC. So PC is equal to this is equal to Na. So if you do simplification, you will find an expression like this. Okay. So EF minus EV, EF is equal to EB plus KT log NV divided by Na. Okay. So we can say that যে নরমালি যদি ইলেকট্রন জাম্প করে এখানে চলে যায়, তার মানে হোল পেয়ে যাব আমরা, কিন্তু অ্যাবসলিউট জিরোতে এখানে যেতে পারছে না, কিন্তু সামহেয়ার হিয়ার স্টেট লাইন হবে, সামহেয়ার হিয়ার, দিস ইজ ইয়োর EF. So this is your conduction band, this is your valence band, this is your acceptor level somewhere here, this is your EF. Okay, this is your EF. So electron এই amount of energy যদি পায়, then এখানে হোল তৈরি হয়ে যাবে, আর এখানে ইলেকট্রন চলে যাবে, গিয়ে বন্ড ফর্ম করা যাবে ডোনারের সঙ্গে। ওকে, কিন্তু নরমালি ইলেকট্রন যেতে পারছে না, মানে somewhere here. So this is your EF. Okay, and you can see from this expression also. So this is the idea of Fermi level in pure and both p-type as well as n-type material. Okay, we will discuss this topic later. This is for related to PN junction. Okay, now we are not discussing about junction, so we will see it later. Okay, now carrier concentration in extrinsic semiconductor in terms of donor and acceptor impurity concentration. Sorry, for an intrinsic semiconductor, already we know that Ni is equal to Pi is equal to, say, this is just for nomenclature, N is equal to P, whatever may be. Fact is that the number of electron concentration in conduction band equal to number of hole concentration in valence band. That means Np is equal to Ni square, Pi square, we know that. Now, let us consider a general system containing atom of both groups 3 and group 5. That is having valence electron 3 and valence electron 5. We are adding both acceptor impurity as well as donor impurity in the same system. And say Na is the concentration of acceptor, means group 3 atom, and Nd is the concentration of donor, that is group 5 atom. Then we assume that, say, both acceptor and donor atom are in ionized state. Okay, so we assume that both are in ionized state. In that case, from the principle of conservation of charge, actually material as a whole is neutral, because your semiconductor piece, যদি তুমি p type impurity, n type impurity যদি দাও, it does not mean ki your material will be charged. As a whole, your system will be neutral. Okay. Now, since again your material consists of electrons in conduction band, then acceptor impurity, donor impurity, and hole in valence band. The hole having positive charge, donor impurity having negative charge, Na acceptor, they can also take an electrons on a ulta policy. Donor, they can give electrons, that means they are positively charged. Okay. Hello. আচ্ছা হ্যাঁ আসুন আমি Okay, sorry, important phone এসে গেছিল anyway. আচ্ছা, so in case of say let us what we did, we assumed a piece of semiconductor where both donor as well as acceptor impurity are added. Okay, and this is the number of acceptor impurity, number of donor impurity. So acceptor impurity are ionized, that means it accepted one electrons, so it's negatively charged. Electrons are already negatively charged. Hole positively charged. Donor ionized, that means it has already given one electron, so we can say that this is ionized, that means positively charged. So since as a whole the system piece of semiconductor is neutral, okay, so we can say that in terms of principle of conservation of charge, this n plus na, that is total negative charge, must be equal to total positive charge, p plus nd, so that totally system is neutral. Okay, now from here, in case of intrinsic concentration, np is equal to ni square or pa square, so we can put here n is equal to ni square divided by p, because np is equal to ni square plus na plus p plus this is okay. Then we can just do some simplification and can have an expression like this. Now we can write a quadratic expression or equation like this, and you can have two solutions of these equations because it's second order. P is equal to this minus b plus minus root over b square minus 4ac divided by 2 এটা থেকে. So you can have an expression like this. Okay. Similarly, if you replace p by ni, p by ni, that is ni square by n, then you will have an expression for ni square in terms of p, sorry, n, and let's see. এক মিনিট দাঁড়াও, রাজদা Okay, so in that case you will have an equation in terms of n as variable, that is ni squared. So similarly we can have solution for n is equal to like this. Okay, now in case of okay, now in case of n-type material, if it is n-type, we assume a general case consisting of both Na and D. Now, and then we found out expression for P like this, N like this. Now, we assume that the system is n-type. Jodi n-type hote hoy tale kita korte hoibo ND should be very very higher than Na. That is Na almost equal to 0, because for n-type system you will not add Na. Okay, in that case ND is very very higher than, greater than Na. So you can write this n is equal to nd minus Na plus minus root over nd minus na whole square plus. What's up? This is for low doping. Low doping means you are adding very low number of donor impurity. Okay, but if you add higher number, then what will happen? Then nd minus Na almost equal to nd. Okay, Nd minus Na almost equal to Nd, because Nd very greater than Na. Okay. Similarly, for p-type material, Na acceptor তোমাকে বেশি অ্যাড করতে হবে, Nd negligible. Okay, but for low doping মানে impurity, number of impurity is very less, is acting as almost like intrinsic semiconductor. Okay, but if you is moderate or a higher doping, okay, moderate also, this Na minus Nd whole square is greater than Ni. Ni means intrinsic concentration. Intrinsic concentration mainly for impure system is due to room temperature or something like that. Okay, because for impure atom, concentration is majority carrier is mainly due to doping. Okay, and Ni is mainly due to rupture of covalent bond, equal number of electron and hole. Okay. So for high doping, again P is equal to almost equal to Na, because Na minus Nd almost equal to Na. Okay, for very good or doping. So we can conclude that for highly doped system, if it is n-type material, then Nn means electron concentration in n-type material is equal to Nd. This is our initial assumption that if n-type material is mainly created by adding donor impurity, and number of donor impurity is equal to the number of electron concentration in conduction band. Okay. Now Pn is the whole concentration in n-type material, and in principle this is very less. This is minority carrier, and this is equal to Ni square by Nd. Nd is very high value in n-type material because you are adding, and Ni is the concentration due to rupture, that is minority, this is less. So P small amount divided by big, so Pn is also small, that this because this is minority. Okay, here again Pi square divided by Nd same. Okay, now p-type material, Pp is equal to Na. Okay, this is good, our initial assumption. Each acceptor atom will suck or take one electron from the valence band by breaking one covalent bond and leading one hole. So ideally it should be equal. So this is okay, and you can see from here also. Okay, Na minus Nd plus minus Na minus Nd whole square plus Ni square. If it is highly doped P system, then Na is very higher than Nd, and also Ni square is very less than this. This is because Ni square is mainly minority carrier, so we can neglect this with respect to this one. Then root ta minimize hoye jabe. Now Na minus Nd plus minus Na minus Nd. Okay, so if you take minus, তাহলে এটা 0 হয়ে যাবে, বাট হাইলি ডোপড এটা 0 হতে পারে না, মানে নো ফিজিক্যাল মিনিং। কাজে প্লাস নিতে হবে, প্লাস যদি নাও তাহলে Nd বাতিল হয়ে যাবে, গিয়ে তোমার twice Na divided by 2. Okay, that means P is equal to almost this one. Similarly, Np, number of electron concentration in p-type material, is equal to again Ni square by Na. Okay, this is এমনি হয় যে Ni square is equal to Np into Pp. Pp মানে হচ্ছে তোমার whole concentration in p-type material, but Pp is equal to Na. তাহলে Na এখানে বসিয়ে দিলে As পেয়ে যাচ্ছ তুমি, আর Ni is very less, Na is very high, so Nv is very less, minority carrier. Here also same. Okay, Pi whole concentration due in p-type material due to rupture of covalent bond, মানে minority carrier. So this is very small, this is higher, again this is small. Okay, so this is feasible. So we can say that in impure atom, number of electron concentration in n-type material is equal to the number of donor impurity, and number of hole concentration in case of p-type material is the equal to the acceptor impurity. Okay. Now we'll move to the next topic, conductivity in semiconductor. This is a general expression for current density in any material. Current density is equal to NEV, where N is the carrier concentration, E is the charge, or V is the drift velocity. Drift means dhakka. And this drift velocity in case of for conduction, because you are applying some field. Okay, so it's dhakka is given by the field, push is given by the field. So drift velocity is proportional to the E on field, and is equal to mu. Mu is a constant. We say that this is mobility. So when you apply unit field, then the drift velocity acquired by the charge particle is known as your mobility. Okay, so this constant characterize the mobility of carrier in a particular material. The unit field dile ki poriman drift velocity lab korbe charge particle, tar mane ki poriman current hobo. Okay, so therefore comparing this and this, we can write in a common expression like J is equal to NE mu E is equal to sigma E, where sigma is equal to NE mu. Charge concentration, charge of the carrier, and mobility. It is called conductivity. So conductivity is a combined effect of charge of the carrier, number of charge, and the mobility. Okay. Now in semiconductor, we know that there are two types of carrier. One is hole and one is electron. And also the mobility of both these two carrier charge particle is different. So obviously there should be two different current. One is due to electron, another is due to hole. So J is equal to Jn plus Jp. So you can write Ne mu n E. You are applying field to a semiconductor consisting of both electron and hole. So field is same. You see E. Charge, both hole and charge is E, and N is the concentration of electron. Here N is the P is the concentration of hole. So concentration and mobility is different. And already ami bolechi je mobility kano hole are yet alada. So from this you can just simply common theorem likhte paro is equal to sigma s E. Therefore sigma s when conductivity in semiconductor age chilo N mu E in case of conductor, but here N mu N plus P mu P into E. That means it conductivity has two factors, one due to electrons, another due to hole. Okay. Now if it is intrinsic semiconductor, then N is equal to P. In that case we can write conductivity in case of intrinsic semiconductor is equal to Ni, and N or P same, equal to mu N plus mu P E. Okay, this is the conductivity in semiconductor. Now total current in a semiconductor. So this is due to drift of carrier, that is conduction current. Okay, so this is one type of current. In addition to this current, transport in semiconductor charge carrier in semiconductor may be due to the diffusion also. Okay, so this gives a current, we say it conduction current. Another factor in conductivity is due to diffusion. Okay, so if you apply field, then your charge carrier will move. This will constitute a current. We say this is conduction current. Okay, where conductivity is like this. Okay, now we say that in addition to this, here again a movement of charge carrier is possible without field, and this is due to diffusion. How? Normally in a semiconductor there may not be a uniform concentration of carrier or particles. Okay, that is concentration or distribution of carriers is non-uniform in the semiconductor. Okay, and due to temperature, they are in random motion. Okay, so since there is a non-uniformity in charge carrier, so let us consider a system of having hole, that is p-type material. Okay, and let us consider an imaginary plane, say at x distance from the origin, and consider that at a particular interval of time, the concentration in this side of this imaginary plane is higher than this side. Okay, so it's possible to have a imaginary surface or a condition that the either side of this surface the concentration is different, since distribution is not uniform. Now, due to thermal agitation, thermal energy, the carriers or holes are in random motion. If there is uniform charge distribution, then random motion, net resultant motion in a particular directions could have been 0. It will balance. The x direction একটা particle যার উল্টা দিকে আরেকটা গেল, যদি ইউনিফর্মিটি থাকতে হয়, তাহলে in that case এটা দুইটা মিনিমাইজ করে net resultant 0 হয়ে যেত. However, here since distribution is not uniform and due to this non-uniformity, যদি এরকম হয় যে কোনো একটা পার্টিকুলার প্লেনের বা একটা লাইনের এক সাইডে বেশি এক সাইডে কম, তাহলে এই ডিউরিং দিস নর্মাল মোশন there could be a situation যে কি এই সাইড থেকে এই সাইডে বেশি net resultant movement of P or hole is higher than this direction. And এখানে বেশি আছে, বেশি থেকে কমের দিকে যাইব, this is diffusion, due to diffusion. Okay. And this movement due to non-uniform distribution within a semiconductor constitute a current. This is true for both hole and electrons. Okay, so this is known as diffusion current, and this current is proportional to the concentration gradient, that is dp dx. dp means change of hole with respect to change in dx, x. dp dx, this is called concentration gradient. Then E is the charge, okay, and dp is a constant. This is known as diffusion constant or diffusion length, and each characterize the material. The material মধ্যে এই যে charge distribution যে non-uniformity, this extent of non-uniformity, দুইটা material নিলে দুইটাতে non-uniform system দুই রকম, এই যে difference, this will dp will differentiate this, okay, this constant, and it depends on the material. Okay, so in terms of for p-type material, we can say that the diffusion current Jp is equal to minus E dp dx. dp dx is the concentration gradient, dp is a diffusion constant, E is the charge of hole. Minus sign indicate that যে higher concentration এর দিকে lower concentration দিচ্ছে, তার মানে concentration decreases with increase in x. That's why minus, মানে p decreases with increase in x. Okay, similarly for hole you can have an expression like this, but here this is positive because একটা minus হচ্ছে due to decrease in concentration, আর একটা minus হচ্ছে due to negative charge. Okay, due to negative charge of electron. So দুইটা minus মিললে plus হয়ে গেছে, E dn মানে diffusion constant for n-type material, dn dx. Okay, so this is diffusion current for hole, this is diffusion current for n-type material. Okay, therefore we can have an expression for total current contributed due to conduction, that is due to field, and diffusion. Diffusion of charge particle or drift of charge particle. So this is due to drift of charge particle in types of p-type material, and this is due to diffusion. So this is the total current in types of p-type material. This is total current in terms of n-type material. Okay, so this is the total current in the semiconductor, and this has two components. One is due to diffusion and another is due to conduction, that is applied field. Okay, so আজকে আমরা এখানে শেষ করব. So if you have any query, you can ask. বিদ্যুৎ?
Yes, sir.
হ্যাঁ, আজকে তো ক্লাস এখানে শেষ করব. কাজে যদি if somebody of you want to ask something or any query, you can raise, or সামনের দিন ক্লাসে প্রথমেও ডিসকাস করতে পারো whatever you want. ওকে, তো পড়বা বাড়িতে?
Okay, sir.
ঠিক আছে, তাহলে কি বন্ধ করে দেবো?